Okay, let's continue. So today we're gonna see the lecture on search trees. Okay, so search trees are new data structures that are going to allow us to do some efficient operations on a data structure. Um, um, well, basically some efficient dictionary operations. We will see what all that means. So we're going to start by defining what's the dictionary. So a dictionary is an abstract data type, okay, which is basically a collection of elements. Okay? A dictionary is just a collection of elements, okay? So we have lots of elements, they together form a dictionary. We do not know how these elements are stored or anything. They are basically, it's just a collection of elements, 1, 2, 3, etc. The elements are records. Each record has a key and has a value. If you remember at the beginning of the sorting lecture, we said that what we want to sort are elements. Each element is identified by its key, okay, and it has a value as well. For example, we said elements can be students. A student can have many things in it, or many fields. A student record can have many fields like name, ID, date of birth, GPA, registered courses, status, lots of things. And we are going to use one of these as the key. For example, ID. Now, the rest of the fields are the value, okay? So we are going to look at the record, pick one field, we call it the key, and the rest we just call it value, okay? So a dictionary is a collection of elements. Each element has a key that we are going to use to identify the element, and has a value which is like whatever is remaining, okay? So that's what a dictionary, a collection of elements. Now, this collection of elements, we are interested to do three operations. We are interested in searching for an element, lookup or search. We're interested in searching for an element. We are interested in inserting a new element, and we are interested in deleting an element. So lookup dk, basically we are saying I want to search for the element with key k inside the dictionary D. Dictionary again is just a collection of elements. Okay, so you have a software, and the software used in a supermarket. So the software has a database, let's say of customers, if they do, or products. So all these, the products, for example, they are elements. For example, they are elements, and the dictionary is actually the collection of all these elements. Okay, and we want to be able to search. If you work in the supermarket, you want to be able to add. I mean, if you work in the management of the supermarket, you would like to add a product to the supermarket. There is a new product. We need to insert it. There is a product which is discontinued, so we need to delete it, and we need to find a particular product. So we want to retrieve product with ID whatever to find how many instances we have in stock, what is the price, etc. Okay, so the dictionary is a collection of elements identified by their keys, and they have values. So we want to be able to search for an element. We want to be able to insert an element. Okay, insert in dictionary D the element which has value k, key k, and value v, and we also want to be able to delete from a dictionary element which has key k. Okay, So once we delete the element with key k, obviously the whole record is deleted. Okay? So I am going to be quite I'm going to give you like basically just to check the understanding. It's something very simple. That's our initial dictionary. It has elements with key 1 and 2 and 3. So when this is dictionary D. So when we say lookup D1, this is going to tell us, this will return the element with key 1. Okay, so it will return 1. If we say lookup D2, it's going to say null. There is no such a thing. If we're going to say delete the element with key 2, then this becomes basically that after deleting 2. If we say insert element with value 4, with key 4 and value whatever, then we add the element 4 which has a value in it as well. Okay, so this is just the operations and what happens to the dictionary. So this is an abstract data type, like we have seen stack or queue. So we still need to implement it. Okay, in stacks and queues, they are abstract data types, and we implemented them using arrays and linked lists. And we're going to do something similar. That's the dictionary, and we need to implement it using the concrete data structures that we know about, which are arrays and lists. Okay, so we're going to start with the array. Okay, we're going to start with the array. So the dictionary, we want to implement the dictionary in a concrete data structure such that the operations are efficient, because this is what matters. We want the operations to be efficient. We have a dictionary, we perform a lot of lookups, a lot of insertions, and a lot of deletions. The dictionary is always being updated. We always search, we always add things, and we always remove things. So let's start by the array. Now, a little bit more complicated than the stack. Now we have a sorted array. We know that we know about sorting. So let's say we choose the unsorted array to implement the dictionary, or choose the sorted array to implement the dictionary. Now what does that mean? What does it mean to choose the unsorted array? That means when we basically the elements in the dictionary are stored in a non-sorted array. So dictionary initially is empty. Okay, so dictionary initially has nothing, and we are going to represent it with an array. So initially the array is empty. Okay, let's say we insert 1. So we are going to put it here. And then we insert 2, we're going to put it here. Okay, we insert element 10, we're going to put it here. Insert element 3, it's going to be here. Search for element 10, then we have to look for it inside this array. Delete element 1, we have to delete that and do the required shifting. So this is what it means to use an unsorted array to implement the dictionary. Now, using a sorted array to implement the dictionary, that means the dictionary initially is empty. So we insert 1. Well, we insert the key 3. So it goes here. And then we insert the key 5. So it goes here. We insert the key 1. We have to to put it before 3, so we have to shift 5 over here and 3, because we need the array to be sorted with respect to the keys. Okay, so this is what it means, and obviously deleting requires the shifting, etc. So this is what it means to use an unsorted array to implement the dictionary, or to use a sorted array to implement the dictionary. Now, let's go back to the table and try to see why this table is correct, or whether I'm just telling you anything here. Okay, so I'm saying lookup in an unsorted array. If we implement the dictionary as an unsorted array, and we try to perform a lookup, it's going to take big O of n. Now somebody explains why.
The index 0 has the biggest element. We have to shift n times to put it in the right place. The last index.
Say it again. Sorry, again.
The index 0 has the biggest key. We have to shift it to the last index in the worst case.
Okay, why do we have to shift it?
Index in the worst case.
Okay, why do we have to shift it?
To make it sorted.
Okay, but this is an unsorted array.
You have to traverse all the elements in the array.
Yeah. So I think the first student was confused about sorted and unsorted. The answer is yes. In the worst case, in order to search, maybe the element we are trying to search is the last element in the array of size n. So maybe it's there. So in the worst case, takes big O of n. Inserting an element, because it is a non-sorted array, we can insert it anywhere we want. Now we can choose where we insert. We can insert at the beginning of the array and then pay the cost of shifting, or we can insert at the end of the array. So every time we have a new element, we insert it at the end of the array, just like I've been doing now when I was explaining the implementation of a dictionary in an array. Okay? Now if we insert at the end, we do not have any if we agree that insertion is only done at the end of the array, then it's going to cost us constant time, because we do not need to do any kind of shifting. If we were inserting at the beginning, yes, that will be big O of n. But here we have a choice. We want a dictionary to be as efficient as possible, so we choose. I mean, we are free. We are going to say insertion is happening at the end of the array, so it's going to take big O of 1. If you remember, when we discussed insertion in the array earlier on in lecture 3, we said it's big O of n, and that's correct, because we were considering the worst case. Okay, we were considering the worst case. Insertion can be anywhere, so it's big O of n. But here we are making a choice. We're saying, look, we are going to be clever. We are going to only insert at the end of the array. So we are looking at a very specific version of insertion, which is inserting at the end of the array. Now, delete is big O of n, and it's quite clear why, and that's because because of shifting. We might, if we're deleting the first element and the array is full or almost full, then we can have big O of n shifting operations. Now let's move to the sorted array. We are searching in the sorted array, and I'm writing big O of log n. Why? Have you seen binary search before? Did some of you not see binary search before? No? So binary search is familiar, okay? So is it clear why it takes big overflow again? Okay, so binary search only works on a sorted array. It doesn't work on a non-sorted array. And what we are doing in binary search, so that's an array, okay, let's make it simple. 1, 3, 4, 5, 6, 7, 8, and 9. And what we array, okay, let's make it simple. 1, 3, 4, 5, 6, 7, 8, and 9. And what we do in binary search, let's say we are looking for item. We are looking for the item 7. So what we do in binary search is we are going to always try to see the middle element and try to locate the item with respect to the middle element. So here the middle element, let's say, is 5. Now, is 5 equal, so we are searching for 7. Our objective is 7. Is 5 equal to 7? Okay, let's search for 6. Is 5 equal to 6? No, it's not. So now we are going to do binary search here. And we are going to jump to the middle element. Is 7 equal to 6? No. But it is bigger than 6, so we are going to search right here, and we find 6. Okay, so you have a huge array. Each time you pick the middle, each time basically you are looking at half the sequence. Pick the middle, compare with the value you're searching for. Depending on the comparison, either go here or go here. If you go here, again pick the middle, go here, and we have seen that when you halve the input, when you divide the input into halves every time, the number of steps become logarithmic. For example, let's say we play the following game, which is like binary search. I tell you, in my mind, okay, I have a number which is between 0 and 1 million, okay? So in my mind, I have a number between 0 and 1 million. And I'm asking you to guess what the number is. And the only question you are allowed to ask is it bigger than some number or is it smaller than some number? So what's the first number you can think of? So I have a number in my mind and I'm asking you to guess it. And I am allowing you to ask me one specific question. The question should be in the form, is the number in your mind, is it larger than this or smaller than this? So what is the first number you use?
500.
Yeah, 5. So the first one you're going to say, is it less or equal than 500,000? And then I tell you it is less than 500,000. So what's your next question? Yeah, that would be your next question, 250k, and you continue, and the number in my mind actually was 1. So how many questions are you going to ask me? So about, in this case, about how many questions you're going to ask me here? About 20, okay? Log 2 of 10 to the 6 is almost equal to log 2 of 2 to the 20, which is almost equal to 20. So you will have about 20 questions in order to find the number I am guessing in my mind. So this is because you have always picked the half. You have reduced the problem into its half. If you were not clever and instead asked me, is the number larger than 900,000 or smaller? and then 800,000, and then 7. Is the number larger than 900,000 or smaller? And then 800,000, and then 750 or something. So you end up not halving the problem into two equal parts, and this will require you more than 20 steps to guess. So that's the spirit of binary search. So each time we're going to halve our problem into two equal parts, and this is going to give us the log n performance. Now, inserting inside a sorted array, I'm saying is big of n, and this is the answer that we got at the beginning. Basically, if we are inserting a key which is smaller, let's say the dictionary is sorted into, or the array which implements the dictionary is sorted in ascending order, and now we are inserting a key which is smaller than all other keys, so it has to go in the beginning, and this requires us to do a lot of shifting, so it's big of n in the worst case. Deleting is similar to the unsorted array. We said we cannot afford to leave empty slots inside the array because it's a contiguous structure. So once we delete something, we have to glue it. Gluing means we have to shift elements either to the left or to the right, depending on the scenario of deleting. So deletion again is going to be big of n. So this is the result of using an array in its sorted fashion and unsorted fashion. So let's move to the linked lists and do a similar study. Unsorted, lookup. I'm saying lookup in an unsorted list is big of n because
Have to follow the pointer until we get there.
yeah, can you repeat it in a more confident tone?
We have to start from the beginning and follow the pointers until we get the element we want.
Yeah, correct. I wanted you to say we have to start from the beginning until, because in the worst case, we have to follow all the pointers until we reach the element we are searching for. Okay? So don't put it as a question, okay? Show some confidence, okay? Give it the right tone, okay? To be like a good answer instead of just asking a question. So, lookup, correct, takes big O of n. Insert. Insert is going to take big O of 1. Can somebody explain to me why?
Because we're just changing the pointers.
What is the location? Okay, if we keep the tail pointer, we do it at the end, or we can do it at the beginning. It's an unsorted list. So we have the head. If we keep the tail pointer, we do it at the end, or we can do it at the beginning. It's an unsorted list. So we have the head, and we just put an element at the beginning. It doesn't matter. So the head points to the current first element of the list, and all we have to do is basically to change the pointer to point to the new element and new element to the previous head of the list. So it's big O of 1. Now delete. Okay. Here is another confusion for you. In lecture 3, when we looked at delete and insert, we looked at them as operation, as basically we did not account for the time that it takes us to reach the element to be deleted. Okay, so in the previous in lecture 3, because we were only considering the complexity of the exact operation. Okay, it wasn't a dictionary operation, it was just the delete operation of a linked list. For example, let's see. So we said that deleting an element, for example deleting that element, we said it's big of 1 because we only have to make this pointer point to this one and break this pointer. So this is big of 1, of course. Now in the dictionary operation, but we did not count the time to arrive to this part. Okay, so this is a list that there is 100 elements, and this is the one to be deleted. So we did not count the time that we have to traverse the pointers to arrive here in order to break the pointers. Okay, we did not count that because it's not part of deletion. It's not part of deletion because deletion is just this. But in dictionary operation, we cannot just say deletion is just this. Deletion is one operation. So when I write a function, when I say delete an element, part of deleting it is also searching for it. So we search for the element, find it first, and then delete it. So this is why when we talk about dictionaries, we mix lookup or we integrate lookup inside deletion itself. Because before deleting, we need first to find the item we want to delete. So lookup is part of delete when we talk about dictionary operation. When we talk about the linked list as an operation, as a concrete data structure, and we separate the actual deletion from the time it takes to arrive to the element to be deleted. Okay, so that's something we have to be aware of. So delete something with the key. We first have to arrive, which we know takes big of n, and the delete itself is easy. It's big of 1. Okay, so this is the difference. Delete in a linked list is regarded as one micro operation. You just manipulate pointers. The delete in the dictionary is a macro operation, which also includes search or lookup, if you want. Now, sorted list, lookup, we cannot say it's big of log n because we cannot do binary search on a sorted list. We cannot jump indexes like in an array. We cannot say now we are suddenly going to go to the pointer at the position 500,000. We cannot do that. We have to actually go pointer by pointer because they are like memory addresses. Insertion, we have to find the right place to put the item. Okay, if the item is in the middle of the list, for example, if it's near the end of the list, so we still have to move in order to find the item to be inserted. And delete is also big of n because we have to first find the item in big of n, and then deletion is big of 1. So big of n for lookup and big of 1 for actual deletion. So make sure you don't confuse the delete as one little operation, or the insert as well as one little operation in a concrete data structure, with insert and delete as a complete operation in a dictionary, which also includes lookup. So this is the table that we have reached at the end. So these are the dictionary operations, and these are the complexities of the dictionary operations given the data structures that we have seen. Now, can somebody tell me and explain why? Okay, we can all agree what is the worst of these. So which one is the worst, just to check? Yeah, sorted list is the worst because it's big O of n all over. Now, we can also agree that unsorted list and unsorted array are the same. So which one is better? So unsorted list, it has a time complexity similar to unsorted array. But which one is better? Are they the same, or someone can be better than the other? Why? Yeah, exactly, thanks. Because we do not waste space on pointers, and also we know that arrays they benefit from cache memory because they are contiguous data structures. So sorted list, we can classify it, so there are 4 of them. So this goes as number 4. Now this one is better than this. So between this and this can be, let's say, 1, and this can be like 2, but we still need that. I mean, how does that come? Okay, so this is better than this is better than this, but we still need to figure out which one is better. Is it this one or is it this one? And sorted array is better? Sorted array is better? I have asked the only 2 possible questions. How can it be no for both? So, between sorted array and unsorted array, which one is better for implementing dictionary? In your opinion? Okay, so who says sorted explains why? Who says unsorted explains why? So who thinks yes here? And who thinks no? And who's not thinking? Okay, the answer is you cannot really tell. You cannot, because so delete is the same for both of them. However, lookup and insert, it's hard. I mean, is your system going to make a lot of inserts? Is it going to make a lot of lookups? Is it going to make a balanced number of lookups and insert? Is the complexity of lookup or the constant factor of lookup or something like that, There are lots of considerations. It's not easy to compare these. But what we can say is that they are still not good. I mean, in order to perform a lookup here, we take big O of n. I mean, what if our dictionary contains 1,000,000 elements? Every time we search for something, we're going to spend 1,000,000 steps. Every time we want to insert something here, we're going to spend 1,000,000 steps. And every time we delete, we're going to spend again 1,000,000 steps if the input size is 1,000,000. Obviously, that's not good. And that's why we're going to come up with a new data structure that we call trees. And it's about too late to start talking about trees. So we can use the last minutes to answer any questions you have concerning this lecture or the previous one. So as a quick summary, what we have seen today is in the second lecture, is the dictionary abstract data type. A dictionary is a collection of elements, and we are interested in 3 operations on these elements: lookup, insert, and delete. And we want these operations to be as efficient as possible. We have considered using the concrete data structures that we know about already, which are arrays and lists, both in their sorted and non-sorted status, and we reached the conclusion that they're not quite enough for our needs, because we cannot afford big O of n for operations which can be very frequent. We are fine doing something big of n if we are sorting a sequence once in a while. Once we sort a sequence, that's it. But a dictionary, we need to make lookups and inserts and deletes quite most of the time. So we cannot afford big of n all the time. So it needs to be more efficient than that. And this is why we are going to see a new data structure, which is trees, in the remaining of the lecture, which is going to happen next week, if things go well. Now, do you have any questions regarding this lecture or the previous lecture? You obviously just want to go, yeah. All right, see you next week.